In this part of the lecture, we're going to apply this principle of conservation of energy to something that is called simple machines. Now, simple machines are things that you may have learned about in grade school, but you may not have learned that they're fundamentally based on the idea of conservation of energy. And specifically, we're going to be talking about work. You put work into a simple machine and you get work out. So what is a simple machine? A simple machine is a device that can multiply and or change the direction of a force. And whenever you have a simple machine, the work or the energy is always going to be conserved. In other words, the work that you put into the simple machine is going to be equal to the work you get out. Here are some of the examples of some of the more famous simple machines. And as I said, you may have learned about some of these in grade school, but either way, we're going to look at some of them today. One example of a simple machine is the lever. Another is the pulley. Yet another is the inclined plane. Then there's the wedge and the screw. And we're not going to look at all of these in detail, but we're going to look at a few of them just to kind of get the idea of how simple machines work and how they're related to the idea that work and energy are conserved. Now, the first example that we're going to talk about is the lever and the fulcrum. So the lever is basically just a long bar or a long plank, and it's got a pivot point that supports it, and that pivot point is called the fulcrum. And of course, you could slide the pivot point back and forth to get a different effect. If you put the fulcrum in the middle, you'd basically have a seesaw. And so if this went down a meter, this would go up a meter. And if this went down a meter, this would go up a meter. And you could think of it teeter-tottering back and forth that way. But if you slide the fulcrum closer to one end or the other, you get a very different effect. And so let's look at the fulcrum and the lever given here. What I have here is I've pushed it down a very big distance on this side, and I get a very small distance rise over here. So I don't get an equal rise because the fulcrum's over closer to the end. And so I push this down a good amount, it'll rise only a small amount. Now, if I'm pushing this guy down, I'm applying a force as I push this bar over some distance. Force times distance equals work. And so that means as I push this guy down, I'm doing work. And the conservation of energy principle that we've been talking about tells us that the work that comes out should be the same work. But what is work? It's force times distance. And so the distance is smaller. In order to keep the same amount of work, the force is going to be correspondingly larger. You're going to be able to lift a heavier load here than you push down with over there. Now, a very common application of this is a car jack. If you want to change the tire on a car, you need to lift it up so that you can pull the tire off. And the usual way to do that is with a car jack. Now, a typical car jack makes use of this principle. It's basically a lever. And so you have this rod here, and there's a lever and a fulcrum. And so as you crank down, it ratchets upward and lifts. But it's as this guy goes down, this guy goes up a little bit. Now, if I push down with 50 newtons worth of force and I move it 25 centimeters, this guy on this side may only move up a quarter of a centimeter, but it's going to do so with 5,000 newtons because 5,000 newtons of force times a quarter of a centimeter is equal to 50 newtons of force times 25 centimeters. You multiply these together, they're going to be equal. And so what you do is you create a situation where you can push down with a little force and get a big force output. Now, there's a rule in our universe. You can't get something for nothing. That's what conservation of energy tells us. And it seems like you're getting something for nothing. You're putting in a little bit of force and you're getting a lot of force out. But what are you giving up? You're giving up distance. You've got to push this guy over a long distance, but it only raises a little bit. But if you keep pushing it down, over and over and over again, eventually you'll lift it up a measurable amount, enough to take the tire off. And so you apply a little force over a big distance to create a certain amount of work, and then the output is a big force over a small distance. And so you've multiplied the force, but it's cost you in how much distance you move through. The next example of a simple machine that we want to look at is the pulley. And a pulley can do one of two things. One, it can redirect a force into a different direction, and in certain situations it can actually magnify a force. And so we have two basic ideas of how this can be applied. So in the figure to the left, you can see that the rope goes over the pulley and then is fixed to a mass on the other side. And so if the person in the picture pulls the rope downward, the box lifts upward. And so you have a downward force input and an upward force output. And that is an example of a pulley being used to redirect a force. But it doesn't give you any kind of advantage. It doesn't magnify the force anything. It just changes its direction. You pull down, it lifts up. Now, that can actually be useful because it's easier to pull stuff down than it is to pull stuff up. So this is very useful if you want to lift something. But even more useful is a movable pulley. And over here is a configuration of a movable pulley. And so you can see that here the rope is affixed to the ceiling and it goes down underneath the pulley and comes up on the other side. Now, when this person pulls up, the tension in the rope goes all the way through the rope to the ceiling where it's fixed. Imagine you had a wall, and in the wall you had a rope fixed to the wall, and you were pulling on the rope with a certain force, let's say 50 newtons. Well, the way that tension in a rope works is that 50 newtons of force is transmitted throughout the whole rope, all the way to the wall. So you're pulling with 50 newtons over here, where the wall is fastened, you get 50 newtons there. Now, if I were to put like a spring gauge to measure how much force is in the middle, so the rope is tied to the spring gauge and then to the other end of the spring gauge into the wall, the spring gauge would say in the middle of the rope, guess what? You get that same force. The force is transmitted everywhere through the rope the whole way. It's the same thing here. If I pull up with, 20 pounds of force, that 20 pounds of force is transmitted all the way through the rope. And so what that means is the rope is actually being pulled up on both sides of the pulley. So you've got the 20 pounds of force being pulled up here and the 20 pounds of force pulled up there. So the lady lifts with 20 pounds of force, but actually the total force that the pulley lifts with is double that because you've got 20 pounds there, 20 pounds lifting up there. So you could actually lift a 40-pound box by just pulling up with 20 pounds of force. That gives you a factor of 2 magnification of the force. You've doubled the force by using a movable pulley. Now, this is the two different ways to use a pulley. You can use it in one case to redirect the force, and in the other case to magnify the force. You can actually combine these. So I've drawn a little picture here, and so I've got two pulleys. I've got a pulley that is fixed to the ceiling and a pulley that is movable. And this movable pulley could be fixed to some sort of load, a box that you want to lift up. And so what you can do is you can have the fixed pulley here redirects the force. So someone can pull down, but on the other side of the pulley, that creates a lifting force for the movable pulley. And so it's, as I said, it can be easier to pull down, so it can sometimes be convenient to pull this guy down, and you get double the force because, again, what you end up with is you get the tension pulling up on that side of the pulley and the same tension pulling up on that side of the pulley, and so you get 2 force output for 1 force input. Now, what's the cost of that? Because nothing in life is free, right? So the cost is if you pull down 1 meter in distance, the box only rises half a meter. So you get double the force, but it's only over half the distance. But if you multiply the force times the distance together, guess what? That number is going to be the same in both cases. Here you can see another arrangement of pulleys called a block and tackle. And this guy on the left here is the way that it normally looks like. And over on the right, this is not the way that you would normally build a block and tackle, but it makes it easier to see what's going on. And so the basic idea is I can pull down here with some force. That force of tension is transmitted all the way through the rope. And so what you end up with is you get a force pulling up like that, like that, like that, like that. And so you get 4 times the force. So if you pull down with 100 pounds, you can lift up 100 pounds of weight. Now, of course, guess what? That means if you pull down 4 meters, it only lifts up 1 meter. So you get 4 times the force, but the distance you move the weight again gets reduced by the same amount. Now, another example of a simple machine is called an inclined plane. And the way that an inclined plane works is a little bit different from the other kinds of simple machines you have. So you have a block, say here, this block here, and if it's on the ground and you want to lift it up to some height, you can imagine one way to do it is to grab the block here and just lift it straight up. And then you have to pull up with the entire weight of the block. Now, if you have it pushed up the inclined plane supports some of the weight of the block. And so you don't have to push with the same amount of force. In other words, you can use less force to lift the block up to this height. But what's the cost? Again, the cost is you have to push it over a longer distance. So you can use less force, but over a longer distance. So again, here's the 2 paths. We can go straight up, and you can see that's a shorter distance, but you have to lift with the full weight because none of the block's weight is being supported by the inclined plane. But if I have my block here and I push it up the hill, up the inclined plane, the floor of the inclined plane is helping you push it up because it's supporting some of that weight. And so it's easier to push it up the inclined plane. You don't need to be able to lift as hard, but you have to push it over a different, longer distance. Now, I want to mention one last idea, because in all of these simple machines, we've sort of pretended that there's no such thing as friction. There's nothing to suck energy out of the system. Remember, the basic principle of this is that the work that you put in, force times distance, is the work that you get out, force times distance. And so you can move something over a smaller distance and get a bigger force. But in reality, there's always something like friction in the system taking away some of that energy and converting it into heat. And so you might not get 100% efficiency. In other words, you might input some force times a distance as an input, but you might lose, say, 10% of that work to friction and heat. And so you might end up with 90% of that force times distance. I hope that idea makes sense, that you might lose some of that work. And so you're not getting exactly out what you put into it, but you can still have this force multiplying effect. And, you know, if you need to lift 200 pounds, but you're only strong enough to lift 100 pounds, it might be worth having to push it an extra distance just so that you can get it up the hill to where you need it to be. Now, when you have a simple machine where you're accounting for things like friction losses or other kinds of losses in the system, where you're not getting all the work that you put in out, we can talk about efficiency. And so efficiency is just this. It's the amount of useful energy that's output divided by the total energy input. So let's say you put in 10 joules. So I input 10 joules of energy, and my output is only 9 joules of energy. So that would be my output. If I plug that into my formula, I would get 9 joules divided by 10 joules, and that gives me 0.9. And usually what you do with this formula is you would multiply it by 100% to convert it from a decimal to a percentage. And so if I multiply that times 100%, I'd end up saying that the efficiency was 90% efficient. And so that means if I put in 1,000 joules, I only get 900 out. I get 90% of what I put in.